All right. Then I guess we're ready to go. Ethan and Kyle, ready?
Very ready. We're excited. Yep, exactly.
All righty. Well, cool. So before we get started, one thing with this final model, we've got some awesome stuff to show you guys. One thing with the final model is it does take a while to run, right? So one of the things that we wanted to demo for you guys, I'm going to go ahead and get started before we go into the presentation, because it'll take about 6 minutes to download this clip, and that way we're ready to go when we get to the demo. So this demo that we'll return to here in a few minutes, restarted the kernels and cleared all the output just so you can kind of see it running from scratch. But this is going to be the application of one of the models we built, right? So this is going to let us use that model to take a full-length tennis match and classify each frame, keep only the frames in class 1, and export an MP4 that's trimmed down to only the frames we want to keep. So just going to get this running so it's running in the background while we get into the presentation here. So step 1, install the libraries, load that trained model that we built, trained model.keras. Should only take a few more seconds here. And once that finishes, I'll run the next one, which is simply downloading a 30-second demo, right? So here's where using the full model, we would normally put the entire length and not trim it to just 30 seconds. But just for this demo, we're going to grab from 33 minutes to 34:20 as just a little 30-second demo. So I'm going to hit run on that. And we should see it start to go here. There we go. And it could take 3, 4, 5 minutes. So while that's running, we can go ahead and get started with the presentation. So, Philip, did you want to kick us off?
Yes, sir. Hey, Ethan. Hey, Kyle. Thanks for joining us today. Welcome. Hopefully, this becomes, we're pretty excited to show you what we got for this today. And let's talk about our agenda first. So, Sebastian, thank you. Let's begin by walking through the agenda. So first, we're going to start with an overview of the project, and then we're going to follow it up by a discussion of the key challenges that we've encountered along the way. Then we'll cover our early milestones, alignment of the project scope. Afterwards, we will dive into the results, focusing on data preparation and video augmentation. And then finally, we're going to share our business insights with you and discuss the next steps. So let's get started with the project overview. Project overview. This was what you shared with us initially in the kickoff call in terms of what you wanted us to do for you guys. So just to reiterate, just read it word for word. The goal of the entire project is to create an end-to-end data product that will help a tennis player or coach determine optimal strategies, point out strengths and weaknesses to provide strategic corrections, and make predictions about future matches and points based on the data. So to achieve this, we integrated technology, including machine learning and AI, with an emphasis on practical and actionable output. Time constraints did limit the scope, but we laid a strong foundation for tennis analytics going forward. So let's talk about our key challenges here. First and foremost, the time constraints, right, was a persistent hurdle. The project was initially designed for a 16-week timeline, but we were tasked with achieving meaningful results in just 8 weeks. The compressed schedule forced us to reevaluate what was realistic and what we could achieve, what was sustainable within the time that we had. Early on, we realized that building a fully operational end-to-end video analysis tool was probably not realistic. So instead, we refined our scope and simplified the objectives. We focused on delivering a prototype that demonstrated the feasibility of the key components like video trimming, object detection, augmentation. This shift required us to prioritize efficiency. For instance, we opted to focus on short, pre-trimmed clips for model testing rather than the full-length matches, allowing us to show some results despite the limited timeline. We had some technical challenges, added another layer of complexity for us. The goal of leveraging computer vision to analyze the match videos was super ambitious and required us to use sophisticated methods. Tasks like the object detection and tracking in the videos proved difficult. So these tasks demanded a lot of computational power and required advanced tools and pre-trained models such as the YOLO V8, which we're going to talk about today. Even with these tools, we encountered a lot of manual prep work and like annotating video frames for training and validation is one example. This process was very time consuming for us, and it was often messed up due to unreliable annotation software. So to overcome this, we experimented with different annotation tools and streamlined our approach to focus on specific tennis elements like players, the ball, and the court boundaries. Another major challenge was our computing capacity. So processing large data sets of high-res match videos, often containing millions of frames, stretched our personal computers to their very limits. So even running pre-trained object detection models on short video clips could take several hours. So full match analyses were out of the question for us on this. Without access to enterprise level infrastructure, that was not going to be possible. So we had to get creative. So for instance, we focused on trimming the videos down to just the ancestral frames for analysis and use sample data to test our models. This allowed us to refine our models more quickly and effectively. And then finally, scope management was another significant challenge that we faced. Early discussions with our team and our advisors made it pretty clear that some of our initial objectives, such as delivering a shot-by-shot analysis, were probably too ambitious for our time frame. So we decided to shift our focus to smaller incremental goals that were achievable within the time. So we prioritized delivering specific features such as classifying frames into keep or discard and accurately identifying the objects in the baseline view, producing insights like ball speed measurements. And this allowed us to ensure that some progress was achieved throughout the project. So given that, we'll turn it over to Becky now to discuss the next part.
So I'll be sharing some of the early milestones we achieved during the first 4 weeks of this project. So first we get into data exploration, and here our main focus was integrating the match videos into Python using cloud-based solutions. And this was a pretty critical step, mostly because these videos serve as the raw material for our analysis. And obviously this came with its challenges. So one of the main ones was breaking down these videos into more manageable time windows. And then we get into model building. So we had multiple approaches to find an effective way to analyze our data. So first, we started off by implementing the convolutional neural network. And at the same time, we were also exploring different strategies that we could use to access the video files, as well as considering different formats and outputs for our models. And again, we encountered some roadblocks here, one of the main ones being inefficient processing times. So here testing just became slower and longer, and that pretty much just highlighted our need to adjust our methodologies moving forward. And then we get into our Gantt chart, and this pretty much just is a visual representation of our timeline and the milestones we achieved again during the first 4 weeks of our project. So just a quick overview of its structure. Here on the left, we have the different milestones and tasks categorized into different sections, as well as who it was assigned to. Up across the top, we have a timeline of the month of October broken down into weeks and days. And then each task is represented by a green bar indicating the duration of each task, and then the red flag representing when that task was completed. So for project kickoff, we had to draft the project proposal, meeting with the performance analytics team, and then discussing our project goals. Very short duration, which is very typical for initial planning steps. And then we had our initial project plan. So coming up with the actual project plan and then drafting up the Gantt chart. This took a little bit longer, spanning for the first 2 weeks or so, but these were crucial for us to stay organized throughout the project. And then we get into data exploration, and Philip really took over here. So this began around the second week, and here we pretty much just focus on determining the data access format and how we would break down if it was by point or by shot. And then again, this extended into the third or fourth week. So pretty much highlighting uh, what I was saying last slide is just the complexity of working with this raw video data. And then we get into model building. So again, how we implemented the convolutional neural network and exploring different output formats and testing different metrics. As you can see, a lot of these green bars overlap with each other, indicating that we were handling these tasks simultaneously. And then lastly, we have the updated project plan. So coming up with the project status report, revising the Gantt chart, and then reviewing the methodology with our advisors, which was completed in the last week of October and pretty much marking a checkpoint for our progress. And now I will pass it on to Ji-Sung.
All right. So previously, our first few weeks of our attempts at model building, just using the basic the convolutional neural network framework, led us to a conclusion that it's not going to work. And this is because the convolutional neural network model is primarily suited for image classification and basic object detections, whereas our goal is to build a real-time detection and segmentation model in live video. So and we had to switch our gears to explore existing models and applications. And we when had to go and explore and see if there's any pre-trained models like applications that was out there and transfer any learnings that we've learned from the first 4 weeks to our next few from week 5 to until now, or find other model types. And our revised project plans are going to be focused on, defining specific video analysis tools to develop boundary overlays, object identification, and ball tracking. And because of this, and also as Philip kind of discussed in the earlier slides, trying to use the entire video was not going to work. We had to cut it down to short video. But like, there are some times where the cameras are not displaying the entire court and then the players. So we had to come up with a different attempt of differentiating the frames, like the ones we want to keep and the ones we don't want to keep. And that's why this led us to like redefining our ultimate step one. And the next slide. And you can see here, this is a week 5 to, until the submission, which is now. And you can see that our new milestones were, attempting a video segment augmentation. Because the basic convolutional neural network was not going to work, we had to find a way to, hey, what ways can we, add boundaries? And Sebastian was in charge of that. And then Ling and I had to come up with, overall object identification, and also like down there we had to find a new strategies for object identifications because the convolutional neural network was not going to work. And this is where the YOLO 8 version 8 comes out later on, when Sebastian and Ling kind of explains our results. But Philip was also charged on, like, how can we make a model so that the ball is being tracked. And Sebastian also worked on trimming the video and pull title from the URL, and this is cool stuff he's going to talk about soon. Real cool. And that made our process real short, and shorter than what we originally expected. And we had to focus on data, and our team kind of basically had to go through that. And now this is a presentation, but before that, we're going to go ahead and move on to our results. And I'll pass it on to Sebastian.
Alrighty, so a lot of the backstory. Let's get to the results. So like Ji-Sung just talked about, right? We kind of had to redefine that step one there. As we're going down this path and realizing how complex it's going to be to add these boundaries and ball and player tracking, and we're looking at a 2-hour long video, we were trimming it down to a perfect 3-minute sample from that core baseline view, right? And as we talked about with you guys a few weeks ago, I mean, that would drastically speed up development, but it leaves one key challenge there, right? What good is the model going to be if it only works on the perfect 3-minute video from the key view, right? So new step one, we need to first prepare the data. We need a way to make sure that we can analyze the video coming in. So we began looking into categorizing the different views of throughout the match, right? You've got the core baseline view with the still camera. You've got the up close of players between points. You've got replays. You've got the overlay of scoreboards. You've got the benches. You've got the crowd. You've got the scenery. You have all these different views going on. But what we realized is that all of the vital in-play footage from service to end of point occurred at that baseline view. So rather than build a multiple classification model to classify 8 different views and start building augmentation on that, we don't need any of those other views. Why don't we just build a simple binomial classification model that says, look at each frame, is this class 0 or class 1? And if it's class 0, let's throw it out. We don't need it. So we built and trained a model in one Jupyter notebook that can take a match URL and it can output a trimmed video that contains only the video time from that essential baseline view. That's also going to allow for better and easier video augmentation, right? If we go in and we're trying to build this network that's going to be able to detect boundaries in players and rackets and balls, it's going to be a million times simpler when those boundaries are not moving with the camera angle, right? You've got one key baseline view to augment for the whole project. So gonna do that live demonstration of this train model and how we use it to trim the full-length match videos. So what you had just seen was me running this download of a 30-second demo, and I'm gonna pull up in the folder what would output there. So in the trim demo, saved at 541, here's that 30-second demo we just downloaded. And what we've got is the key baseline view for a second, and then an up close of the player. And then the key baseline view at the serve, right? And then walks around for a sec, and it cuts back to this up close of the player. We don't want any of that up close of the player, right? So we built this trained model, and here we go back to the next serve from that baseline view. So we built this model, this trained underscore model, that when applied to that 30-second demo will keep only the views, only the time in which we're in the key baseline view. So we've downloaded the video, and we're going to break that 30-second video into frames. And I will hit run on that. That should only take about 5 seconds. And there's 25 frames per second. So 750 frames in the 30-second video. And now we need to classify the frames and only save the ones that are in class 1. And here's where we're pulling that trained model. We're going to take these match frames that have all 750 frames from that 30-second clip, and I want it to apply our trained model to keep only the class 1 frames, key baseline view. And it's going to output the classified frames being only the ones in that view. So I'm going to hit run on that. Now, while that runs, I'm going to share with you kind of what the building of this looks like. It's not going to take too long, just a few minutes here. But what the building of this looked like is our other notebook we'll share with you guys. So what I'm in the middle of is a demo of using the trained model to trim the match video. But here's what it looks like building this trained model. So you can follow the logic and error handle if necessary, right? So while that other notebook's running, this notebook allows us to train a model to classify frames of a tennis match. It's going to create an MP4 that's as short as possible while still containing all those identified views. We're going to export it into a folder of frame-by-frame images. We're going to manually label all frames with binary classes. We're going to train the model with 80% of the labeled ones, test it on the remaining 20%, and export a trained model that can be used in other notebooks to classify the frames of match videos. So, step one, install the libraries. These were all done already. You install your packages, you import your required libraries. You're going to download a full demo being the train plus the test, right? So I downloaded this 5-minute video, and I'm not going to go rerun this code because we would be here for hours, right? But here is that demo. I could show as well length here. It's, length. So here's this 5-minute demo that we downloaded. And this way we've got all these views included, right? It's following the player around, and then he's serving, and then it's a replay, and then, you know, have the scoreboard come up for a minute. We've got some audience in here, etc., for this 5-minute demo. Now, the only thing that demo was missing is that intro, right? The intro we talked about, that's about 20 minutes of just this screen right here. So with that demo video, we've got this 5-minute demo. Now we're going to download, we download that 5-minute video. I'm sorry, 0 to 30, this is the wrong one. I adjusted this code to match the demo. Let me open the actual trim model. I'm sorry, not the demo. So download the full demo, train and test, and that's going to be that 5 minutes at 46:30. Now we need to download a demo of the intro, which I showed you. It's just 30 seconds of that intro. Now we need to download the splits as videos. So you've got the training split being the 4 minutes right after 46:30, and that's going to be the set for training, 80% of the 5-minute video. Now we're going to download the testing split of the video, and that's going to be the last 1 minute. And so that's what you see come up here, as you've got a 4-minute train and a 1-minute test. Now we're going to break those samples into frame-by-frame images and export to a folder. But included in that, we also want to include some screenshots from that intro as well for training. So what we've got is export this training set at 5 frames per second, and go at 4 frames per second on the intro. And so what that does is it's going to export our frames for train, and it's going to be a mix of both class 1, which we want to keep, and class 0. And at the end, a handful of live event screens. Now you see exported 1325 frames. So now do it again with the test set, right? Do the exact same thing on the test video at a frame rate of 5. This time I did the intro at a frame rate of 1. So the same way we did 4 minutes to 1 minute, I just did frame rates of 4 frames per second to 1 frame per second. So 330 go to the frames underscore test. Here you go. Mix of class 1 and class 0, some of the intro right there at the end. And it exported to that folder. Now, here's where you got to leave the Jupyter notebook, right? To train this model, we have to manually classify some images as class 1 or class 0. And so that's where you jump over to a supervisedly dashboard. And so I've got this in here as instructions for another user, but open to project and supervisedly. For both the training and test sets, you got to manually label everything as class 1 or class 0. So in here, you've got the frames train and the frames test. And essentially, you can come in here and create tags to annotate your photos. You guys will not need to do this, right? The model is already trained. But if you wanted to enhance the training or have the next class do this again, here's how you would do it, right? So basically go through each frame of all of our training and test set and say, okay, this is class 0. You can put a hotkey to just do it very quickly with an N. You know, I could hit the N, right, N, right, N, right, and classify all these frames with a tag of class 0 or class 1. What we end up with is now these 1325 for training. We can apply a filter and say tag is class 0. Okay, it's only the frames that we don't want to keep. And flip that filter to class 1, and it's only the frames we do want to keep. Perfect. So we get that back in here, right? We train and test the model. So this code right here essentially takes our annotated data and flips the order of it. So rather than having annotated, you know, labeled frames where they come in separate folders of the images and their annotations being class 1 or class 0, we're now going to run that block of code right here, and it's going to create the train and test data folders right here, where now it's classified into 2 folders of classes instead of images and annotations. It kind of flipped the order that we're sorting there. So once we have all that classified, we can load that data into the model. It finds 1325 images belonging to 2 classes from train, 330 images belonging to 2 classes from test. And now we can build our model. And we ended up actually using a CNN, a convolutional neural network. This looks like something out of one of the classes we've taken, where you've got a stacked convolutional model with max pooling in between, ReLU activation. You've got a softmax activation on your flattening. We're using an atom optimizer and a categorical cross entropy loss function, right? Now here, this actually didn't take too long to train the model. It ran for about an hour and 15 minutes. And what you see is the accuracy after 41 steps through the first epoch was about 70%. It's guessing pretty well. Now you see the validation accuracy quickly hits 1 and stays there. While the model finds its best route, it first hits an accuracy of 100 in epoch 4 and finishes with an accuracy of 100 on the last epoch and says, all right, model training incomplete, exported here. Now this trained model is the key, right? So now we just test it on the test set. We'd only use that 80% labeled. Now let's apply this model and see how well it classifies that remaining 330. So we run this thing, it comes out, it finds 330 images in the test set. Test data was our directory. It runs through, it finds 100% accuracy with almost no loss and gives 5 examples of predictions. Predicted class 0, actual class 0. Predicted class 0, actual class 0. Unfortunately, the 5 in the sample were all class 0, but it's showing that for all 330, it guessed correctly using the prediction from that model. Fantastic. So now we can take this model and apply it in here where we're now done, right? And so this is all we had done so far in this notebook. You've got the notebook I just went through to train the model, and the model comes out. In the new notebook, use this to trim the video. All you need to do is put the URL you want to download right here, right? We hit run on that. It downloaded a 30-second demo. We hit run on this, it broke it into frames. We hit run on this to classify it and save only the class 1 frames. And what came out so far is this classified frames folder. So in our demo, we had 750 items in the match frames. Of course, it's not loading all of them yet. And we end up moving 423 to the classified frames, and it's only that key baseline view. So the very last thing we need is just to throw all those frames back into a video in the correct order. And so I hit run on this last block of code. It runs for 5 seconds, 2 seconds, and says the trimmed video is exported as trimmed demo. Here it is. It just appeared this minute. Here's the trimmed demo. And remember, when I showed this 30-second clip, there were those breaks where it showed the players up close. In the trimmed demo, it's now only going to show the 15 seconds from this key baseline view, and it's going to cut out all the garbage. So right here, you'll see that skip, right? He walks around for a second, and then where it would have zoomed in on him and watched him dribble the ball for a couple minutes and maybe zoomed in on the crowd, it cuts that right out. And we only are watching from that view. So what that looks like on the actual model. The difference being on the actual model, use the model to trim the match video. Same exact code. Input the URL. You could paste the URL of any match you want to trim. It's going to download. It might take, 3 minutes to download. It's going to extract the frames, but now we're looking at 188,000 frames because we're going 25 frames per second on a 2-hour-long tennis match. Now to classify all of them is what is going to take forever. So we're applying that trained model to the 188,000 match frames and telling it keep only the class 1 frames. This took 12 hours and 45 minutes to run. It took a long time to run and process and look at 188,000 frames and classify them as 1 or 0. But step 5, put it back into a video for us. And what we find is this. Here is the full match, 2 hours and 5 minutes long, that has a 20-minute intro of nothing. And then throughout the video has cuts and crowd and replays and up closes and overlaid scoreboards and scenery and all this garbage throughout the whole video. But what the final model does instead is it trims it down to just 51 minutes. And when it plays from the beginning, you're going to see the fading intro screen. Right there, first frame is the fading intro screen. And now you've got 51 minutes just from this baseline view with no garbage. So the only challenge with this, right? This is a great step 1. Now we've got the garbage trimmed out and we can actually start taking the next steps, which Ling's going to talk about in a sec. But before I pass it over, the last thing that I want to quantify is how much data this is really using. So that was the live demo of that trained model. Now, quantifying the data, right? We're looking at 7,500 seconds at 25 frames per second. And so you saw the 188,000 frames being processed. Now, how these image analytic models really work, there are 230,000 pixels in every frame of that match because it's 360 by 640. That's also a low resolution match. And so we're going to have 43 billion pixels across all those frames. Now, each of those pixels has 3 color factors, an R, a G, and a B. And so we're processing with that model what took 12, almost 13 hours, was processing 130 billion total data points. So I threw this in here to quantify as well, right? $10,000 that you could hold in your hand like nothing. 1 million is going to be this stack of cash, and 1 billion, you're looking at 10 pallets of $100 bills. Now times this right here by 130, and that's how many data points we're analyzing with this model and why it takes so long. So with that, I'm going to pass it off to Ling.
Okay, I will take it from here. Okay, all right. Now that we have a full match video with the key baseline reels, I'll walk you through the results of video augmentation using the YOLO V8 pre-trained model for object detection. Okay, so we were trying to, do a custom data set, but we face a challenge, which is the time constraints. It limited our ability to manually annotate large data sets for training and testing. So to address this, we used the YOLO V8 pre-trained model for object detection. This doesn't require extensive custom annotations, allowing us to expedite the process. But using this pre-trained model is, just a general object detection model. So it's not designed for tennis match analysis. So we fine-tune the YOLO V8 pre-trained model, to detect the key objects in the tennis video, which include the players, the ball, and the tennis racket. And the outcome successfully detect these critical elements in real-time match footage. So the key benefit of using a pre-trained model is the quick deployment, and it reduces the setup time and allowing us to integrate the model into our match analysis workflow quickly. So now let's move to show you a demonstration how this works. So this fine-tuned model will identify, these relevant objects by identifying these objects, and we can also track the ball speed, throughout the match. So I will show. Actually, I'm still should be in here. Okay. So here it's an extracted frame without augmentation. So, and then here is the original pre-trained model, but you can see that it's detecting, a wide range of objects, and that is not relevant to the tennis match. So such as the umbrella, the chairs, and all that. So this model is good for general object detection, but it includes a lot of irrelevant detections. So to make this model more useful for our analysis for the tennis match, we fine-tune it to specifically detect the relevant objects. So here is the fine-tuned model to detect just the person and the sports ball and the tennis racket and this model will take either an image or a video and then
Elaine?
output accordingly.
You're still sharing the PowerPoint view.
Oh, okay. Let me see if I have to.
You might just
Okay.
drag the notebook to the other screen.
I only have one screen.
Oh, okay.
Right now, I don't know why it's not sharing.
I think
So
you're gonna click on the screen, not the application.
let me see here, screen. Okay,
When you share
can you see it
screen,
now?
there you go.
Okay, all right, so let me go back to here. Here's the script that it will detect the person's sports ball and the tennis racket. And this code will take either an image or a video and then output accordingly. So if I run this code and it will produce the following. So if I run that, it will produce this result. Okay. So in here, you can see that it's no longer detecting the chairs, the umbrellas and all that, but it's not perfect yet. It's still detecting the audience and also the shadow of the tennis racket, if you see in some frames. So it needs more fine tuning, but we got it to detect the relevant objects for the match. While we were like fine tuning this model, we also noted that we could track the ball speed. So we wrote a script to combine the object detection specifically to the sports ball and added ball speed calculation. So I'll go to the script. So in this Jupyter Notebook code, it's still using this pre-trained model, and then it will take a video, and the end result will be producing a video and also a CSV data file. So this code will take the YOLO pre-trained model to detect the sports ball, and then using the center of the bounding box on the ball to calculate the speed, and also output on the screen, and also log it, on the screen, and also log it into the CSV file. So if I run this code, it will produce a video, and it will produce a video and also a CSV data file that gives us the frame number and also the speed at pixel by second. So you can see it's outputting on the video also. So just like I said, the time constraints and it's kind of limited our ability to fine tune it further to make it more accurate, to detect the objects, and also the because the quality of the object detection is not perfect yet, so sometimes it's not picking up the ball when it should be. So that's why the speed measurement is based on that, picking up the ball and then measuring the center of that bounding box and then compared the frame by frame. So this can be improved in the future, project. So to recap, ball speed is a very important indicator of player performance and match intensity. So by measuring the ball speed, we can gain valuable insight into the player's strength, position, and the overall match dynamics. As you can see, the ball speed is displayed on the video and the speed data is saved in a CSV file for further review. This output can be very valuable for coaches looking to optimize player performance. So now I'm passing it back to Sebastian.
Thanks, Lane. Unbelievable. I can't believe you got the ball speed as well in there. That's something else. All right, so then to wrap this thing up, are you guys seeing the presentation slide?
Yeah, we see
All
it.
right.
We see it.
So to wrap this thing up, you know, business insights and next steps. So where does this go from here? Now you have the tools to trim the full-length match videos down to one key view. You've got the baseline model for object detection and tracking. And so next steps ideally would be improve upon the object identification, make sure it's just the two players and not the persons on the sideline. Dial in that ball object identification, make sure racket shadows aren't captured, etc. Just some fine tuning there. Add back in that boundary overlay. You remember we had a lot of challenges with boundary overlay because we were applying those to the full length match. And it's confusing the model when the boundaries keep moving on the screen. So hopefully that should be a lot easier now that you can have the whole match in a single viewpoint. And once we add those two things, the next steps would be to start determining the actual insights to be discovered, right? What can we draw from this as far as this player has a tendency to, his second serve is always outside, and this player's backhand is terrible, and this player loses ball speed throughout the match. Keeping those insights would really be the next steps now that we've kind of got this framework and once we dial in those last few things. Now, considerations with going forward. So remember the quantifying data example. So many of these models to follow will require many hours to train and run, or just incredible computing capacity, right? Something better than my $400 Asus Vivo book I'm working on here. It's big data, right? And so just as a reminder there, right? Applying that model just to trim, not even the augmentation, but just that trimming model that classified all frames as 1 or 0 and threw out all the zeros. Applying that to just one tennis match required analyzing more than 130 billion data points and took about 12 hours to run, about half a day. Now, the ATP live stream page that you guys shared with us has more than 59,000 events. So if we were just to trim the approximately 20,000 men's singles matches, that would require analyzing more than 2.6 quadrillion data points, right? More than a billion times a billion, right? And I'm sorry, a billion times a million. And running these models for that many matches, 20,000 matches at 12 hours a match, just trimming all of those down to the single view would take about 10,000 days, more than 27 years to apply that model, right? I mean, that's too slow. You guys aren't trying to launch this model in 2052. And so, final considerations. For the next class, if we take it with the next class, as we did with this project, I would say the biggest focus would be focus on working efficient. We spent too much time looking at the entire match video, and we really started making progress once we cut it down and we were practicing our models on 3-minute samples and seeing what we could pull from what and exporting frames to see how we could just do simple image analytics rather than approaching the 2-hour video. And next, whether you guys or another Capstone team, perhaps explore options for outsourcing the next steps, right? We've now got kind of a vision of how much computing and how much time this would really take. We can't wait 27 years. We need the model to work faster than that. And there are bigger data companies out there who could probably run that trim model in a matter of seconds, right? Because they have a room size computer that could do it like that. And so outsourcing options might be a good endeavor as well, as far as getting this product to market quickly, or even in any sort of a reasonable time frame, right? Continuing down this path of trim and augment, it would take way too long before we're pulling actual insights from that tennis match. Last thing I wanted to point out, so want to share with you guys these Jupyter notebooks and the train models, right? And so what we've got for that is going to be, you know, I'll share this trim demo that I just did live where you could really delete these two or really delete these 4 items, and you could yourself run these 2 notebooks that reference this train model to do that 30-second demo on your own computer. You'd have to install some libraries. The instructions are in here. But you could do that on your own, as well as the full trim model that's got that entire process where we labeled the models in a supervisedly dashboard and exported these zipped, labeled train and labeled test folders. And you've got the 30-second intro video and the test split that's 1 minute and the train split that's 4 minutes, the full match at 2 hours, that full demo at 5 minutes, and then that resulting trimmed match at 51:20. And all of the stuff that goes into that throughout these processes with the finished notebooks. Plus, I've got in here as well some of the outputs from the testing. If you had another class trying to error handle, you've got, you know, the first train model that came out. The first one, we hadn't considered that intro yet, and we ran this whole model, and it came out and classified the intro as class 1. And we went, dang it, we got to put the intro in there and classify it as 0, rerun this thing. So you've got some of that history as well. Now we have to add links files as well. And then we'll also be adding the Gantt chart completed in the Excel file. This presentation we're giving right now, as well as Ling's demo that she gave on her PowerPoint. And all of this together, all that data is going to be probably about 17, 18 gigabytes. So we'll probably need a 32 or 64 gigabyte flash drive unless you guys have a better way to do it. I tried uploading to my Google Drive and just instantly was given, you know, the system basically crashed and told me, you've used all your space and shut down before it even began trying to upload all this stuff. So do you guys have like a cloud-based storage system that would be good to upload these to, or would you prefer just a USB drive with all of this output here?
It's up to whatever's easiest for you. We use Dropbox if it can. I think we have the 1,000 gigabyte like monthly thing, so that might be an option if the file formats like will work on there. Because I don't know if it'll do the same thing. So we may end up that might be the only option if it doesn't end up like I don't know how the files will work.
I think I mean, we'll give that a try, but worst case scenario, we'll throw all this on a flash drive and drop it by one of you two. But with the considerations for next steps and you know how we're going to share that stuff with you guys, we can stay in communication, of course, not blocking your guys' numbers. We'll be happy to help you kind of dig through these a little bit and get you set up for the next course if you guys are going to do another capstone, and we'll figure out how to get you guys all this data. But with that, I believe that is the end of our presentation.
It
Thank
looks
you
awesome,
guys.
guys.
Yeah, it was
Thank
super
you so
impressive.
much. I know. I think Kyle and I are both on the same page with this. It's great to see the progress that you guys have made, and like, of course, sorry to use you guys as like the guinea pigs for us, but there's a lot of stuff that you don't know what you don't know until you kind of get in there, and so for you guys to even be able to work through a lot of these constraints that we had, which we had some idea about, but really seeing the scale now of what you guys were able to get through, it's great to walk away from this with like a true proof of concept that I think we can now, whether we're taking this to the next ASU group and saying, hey, how can we make this more efficient, or going to a bigger scale and saying, okay, it's time to look for companies that we can outsource this to and actually like speed up this process. So really everything looks awesome, guys.
Thanks.
Yeah, I same thing. I thought everything was awesome. I was wondering how long the supervisory took for the like however I can't remember how many frames it was, but I was wondering how long it took to label them 01 on all
Oh,
those.
it was about, well, I did it twice because the first time didn't work right and was missing a thing. I don't know. I put in some headphones and listened to an album and a half, and I just sat here going right arrow, yes, right arrow, no, right arrow, yes, right arrow, no. It only took like an hour and a half. It wasn't too bad each of the two times. Um, a little monotonous, but you know, I gotta say once, and these guys will tell you that once we got the trim part of the model running and that bar was actually loading, I was messaging these guys at like 3 in the morning, like, guys, when are you awake? We need to chat immediately.
Super
then-
impressive. I'm stoked that you guys got it trimmed just like that. It looks awesome, and it's like you're saying, that's exactly what's needed if you're going to do any analysis, is that steady like camera angle.
Well, and then I got to give it to the teammates here because I finished the trim part and I thought like, okay, mission accomplished. Now we've got working model. And within a couple days, some of the teammates here are sending videos of the match augmented with ball tracking and ball speed and player ID. And I'm going, okay, we've actually got a working product here to show. So yeah, we were really excited to share with you guys.
Yeah, the nice job with the augmenting. I don't know who was the leading that. Was that Ling? That was very cool. Nice job.
Yeah.
Nice job, Ling. That's awesome.
Well, I wish I had more time actually, to train it on a custom data set, to be able to differentiate the players and then more accurately detect the objects and, be able to do the court boundary and all that. But it was like towards the end of this, like the last 1 week, and I'm like, I don't think I can do even more than that. So as long as I can show you something, I think it's pretty good. So yeah.
Yes, nice job. I'm sure that training that type of model is super time consuming with the like trying to bound out certain stuff, and yeah, I can't even imagine.
Yeah. Hopefully, if you pass it to the next group or something, they can, train on the custom data, and then it'll be, accurately detect the objects, and also can get insights from those.
And if they do want to do that, that supervisory tool I showed is a great tool. Beyond just tags, you can do things like object identification where you can click through one at a time and say, here's the player, here's the racket, here's the ball. Next slide, here's the player, here's the racket, here's the ball, etc.
Yeah.
So that could be a great
Yeah.
tool as well going forward for you guys.
Yeah, I also found RoboFlow is pretty good. I tried it a little bit, and then actually they have auto detection. So I was trying, but I just ran out of time. I just couldn't, explore further. So that could be a good tool also, to be on a robo flow, So yeah.
Thank you for the tips. I think the next steps that you guys gave also were like spot on. I think those were super helpful as well. And I like the visual representation of the data points, like the 130 billion. I like that.
It's crazy to think about how much data these models are really processing, right? And 12 hours, okay, sweet, that's no time at all. It ran while I slept. But now if we want to do 20,000 matches at 12 hours a pop, we're going to be waiting 30 years. So, and that's just to trim them. That's not even pulling any insight out of the video. So you've got a massive amount of data here to work with.
Well, thank you guys so much for the time you guys have spent on the project and for all the meetings and everything. It was really awesome getting to work with you and meeting you everybody. And you guys did it in such a shortened time too. You guys were rapid fire, so that was really impressive. And the output and the presentation was super impressive as well. So congratulations on completing your guys' thesis, and great job with the project. Me and Ethan really liked it.
Yeah, we definitely appreciate all the work that you guys put into it, and we know that it wasn't easy. We threw you guys a huge end goal and not a lot of insight into how you guys were going to be able to get there. So to be able to figure it out and create your own roadmap and work your way through it, find the different challenges, and get us to where we are now. I know Kyle and I are both super excited about it, so we really appreciate it. I think both Kyle and I want to stay in touch with all of you guys. We'll definitely be bothering you with more questions if you're available, and hopefully we get a chance to even work together down the line potentially.
Sweet.
Thank you for providing us this project. We were kind of like, oh no, because the first one that we got was like it fell through, so we're like in a panic mode trying to find another project. And thank you for providing us the opportunity to work on this.
Yeah,
You're
agreed.
welcome.
Yeah.
I hope you guys had a little bit of fun, at least with some of it.
A bit of fun.
Challenging, but it's fulfilling to get something done. So
Definitely.
yeah.
Yeah,
All
like
right.
she said, thank you guys, because my company was gonna have me do the project in about 3 days before we needed to start. They're like, oh, what, never mind. And we're like, what are we gonna do? So you guys really came through for us.
Awesome. Well, I'm really glad that it worked out, and like we said, we're really happy with the output, and we're really excited to like take that and branch further with it, because we think that it's got tons of potential.
All right, guys. Yeah, if you have any other questions, I guess let us know, and we'll get you these deliverables as we figure out how to do that. And anything else before we sign off?
I think that's all. Thank you guys so much. I don't know if you guys have any more finals left, but good luck if you do. You guys will get through them,
Yeah.
and you'll get your shiny degree.
Absolutely.
Thanks again, guys.
All right. Okay. Thank you.
All righty. Thanks,
All
guys.
right.
Thank you
you.
guys.
Bye.
Thank you.